Hello everyone, and welcome to one of my videos on optimization, the very first one. In this video, we're going to be looking at making cost-efficient water cans for the company H2O Go. What they want is they want something that's going to cost them the least amount of money, so use the least amount of resources and materials, hence having the lowest amount of surface area, and they want it to be able to house 1 litre of their H2O Go water. So there's a few things we need to consider, and I've listed a few checkpoints down the side. So from this, we'll be able to find the optimum dimensions to get that least amount of resources, so H2O Go is going to be happy with putting out their cans to the public, knowing that they're making the most profit they possibly can. Okay, so now what we need to work out first is the value of H in context, and H is obviously going to be the height. Now, something important to consider is that the volume of this is 1 litre, and it's good to be able to work with centimetres because we know that obviously it's not going to be metres we're talking about here. I mean, it's not like it's a 10 litre set of water or 20 litre, we're just looking at 1 litre, so we know we're generally going to be working with centimetres here. So if that's the case, 1 litre equals roughly, in fact it equals exactly 1,000 centimetres cubed. So from that, we know that that's obviously going to be our maximum volume, and then we're going to have to be able to subtract something from that because we have a circle at the top. It's either going to be subtract or divide, and in this case it is divide because we need to be able to account for the area of the circle there. If you're looking at a different aspect, not area, then sometimes you may need to subtract values. If it actually curved in a bit and it wasn't an exact tin can, then perhaps you would have to take that into account as well. In this case, it's just the area of the circle, so it's over pi r squared. So again, total volume and the area of the circle, and that gives us our height value to try and optimize this cost-efficient set of water cans. So now, after this, what we need to do is we need to consider the total surface area, because of course that's what we want to be able to minimize. So the total surface area of a cylinder is given by the following: 2 pi r squared, 2 pi r plus h. And we can use the distributive law to be able to expand this. So we have 2 pi r multiplied by r, and that's going to give us 2 pi r squared, and then we have 2 pi r multiplied by h. And we know what h is in context because we actually just worked it out a moment ago. So from this we have 2 pi r squared plus 2 pi r lots of 1,000 over pi r squared. So now we just multiply across the numerator and we get 2 pi r squared plus 2 pi r lots of 1,000 over pi r squared. And here we can see we can cancel pi because it's multiplied by other values, not added, so we can cancel out the numerator and denominator, and we can cancel out one of the r values from the denominator as well. And 2 times 1,000 is 2,000, so we get 2 pi r squared plus 2,000 over r. And that gives us our total surface area. Now think about it, we need to be able to use technology to be able to find this. So we have an input value of our radius, because that's a value we're going to change. The radius will change, and because of that the height will have to change to maintain that ideal 1 litre volume that they want. And because of that we'll have the output of total surface area, the amount of materials we have from there. So our input value is going to be r, so those are going to be like x values when we put them into the calculator. And our total surface area is the output. It's a consequence of changing the radius. So because of that, the total surface area is going to be y. So we can graph this in a calculator as y equals 2 pi x squared plus 2,000 over x. So you can get out your graphics calculator. I'm going to go through instructions for a TI-84 because that's my calculator of preference and the one that I own. So you type in 2 pi r squared, 2 pi x squared, sorry, on the calculator, and then you type in plus, and then you go bracket 2000 divide by x bracket. And now what you do is you'd hit graph. I'm sorry I'm not giving instructions to other graphics calculators, but I'm sure you'll be able to work it out. And for TI users, I'm not sure where it is on the Casio or the HP, but you can press second function table, and then you can scroll across and get an indicator of where the minimum is. I mean, graphically you could change your window to be able to do it, but having it via an actual editor here also helps as well. So now you've got an indicator of where the minimum actually is, either graphically or using the table. You need to be able to position your cursor using the minimum function to the left of and then to the right of that minimum value. So if you go into second function calculate on your TI and make sure you're on the correct function, and then you go left bound, press enter, and then you go right bound of where that minimum is, and you're going to end up with a value, and I'll round it here, but you get an x value of 5.42, and that's going to be equal to the minimum, the ideal radius, I'll put it as. And we get a y value of 553.6, which is, and if we give it in units, that would be centimeters squared, and that would be centimeters, but that is the actual total surface area when it's at a minimum, because again, lowest amount of resources. So from this, we're able to work out the value of h, because we have it relative to r, and we're able to draw what's known as the optimum dimensions diagram. So I'll just clear this off, and I'll write h over here so I don't rub it off, just so I get a bit of extra room. Sorry that that's probably really, really bad and slanted. I'll just fix that. I know some of these are probably slanted, but that was very slanted. So from this, we get a cylinder, and we have a radius of 5.42 centimeters that we were able to work out on our calculator. Therefore, we have a diameter of 10.84 centimeters. And now what we do is we calculate the height. And in order to calculate the height, we go onto our TI-84 calculators, and we go 1000 divide by, then we do a bracket, pi, and then we do another bracket, 5.42 squared, bracket, bracket. And we get a height equal to 10.84 centimeters. Remember units. And you can actually see that the diameter is the same as actual height when it comes to these H2O Go cans. And that is what actually allows us to have the lowest amount of resources with the lowest surface area, those dimensions there. And we can even write underneath, the total surface area of that cylinder is equal to 553.6 centimeters squared. So we've made the most cost-efficient water can. Sorry about that, I almost got tongue-tied there. And hopefully H2O Go will be happy, because of course it's going to be more economical for them and they'll be able to maximise their profits. So there's just a look at one little bit of optimisation. There'll be more videos coming soon, but I hope you enjoyed it, hope you're able to follow along with it. Any questions, write them below, and thank you very much for listening.